Welcome to the future of construction. Forget traditional bricks and concrete for a moment. Imagine buildings that can heal themselves, sense their surroundings, and even clean the air. This isn't science fiction, it's the emerging field of living fungal materials. We've heard about using mycelium, the root-like network of fungi, to create sustainable packaging and insulation by compressing it with waste products. That's impressive, but it's just the beginning. The real revolution lies in keeping the fungi alive within the building material itself. These are called engineered living materials, or ELMs. Think of ELMs as dynamic, functional materials. Recent studies have shown materials combining fungal mycelium with living bacteria that possess remarkable self-healing powers. When a crack appears, exposure to air and moisture can wake up dormant fungal spores or bacteria. They grow into the gap, often reinforcing the repair by creating minerals like calcium carbonate. Researchers have gotten these living materials to stay viable and capable of self-repair for over a month, a huge leap forward. Creating these materials requires sophisticated engineering. Techniques like using special knitted molds allow for complex, strong shapes, improving oxygen flow for the living fungus. Scientists are also using 3D printing methods like direct ink writing to precisely place nutrients, guiding fungal growth to control density, and even create patterns within the material. Imagine printing functional zones directly into a wall. There is also biowelding, where separate living fungal parts are grown and then encouraged to fuse together, potentially forming large, seamless structures. Furthermore, researchers are looking into selecting specific fungal species or even genetically modifying them for enhanced resilience, perhaps to survive in concrete or even break down pollutants. Hardy fungal cells, called chlamydospores, might be key to long-term survival and healing in dry conditions. So, what can we do with buildings that are alive? The most obvious application is self-healing structures. Minor cracks repair themselves, extending the building's lifespan and cutting down on maintenance and waste. Imagine bridges or tunnels that mend themselves, but there's more. These materials could create adaptive environments, changing their structure to filter air when pollution levels rise, or adjusting thermal properties with temperature changes. The fungal network itself could act as a biosensor, detecting stress, moisture, or chemicals. We could even design buildings that actively clean the environment by incorporating fungi that break down toxins or capture carbon dioxide. And looking further afield, the ability to grow structures from lightweight spores could revolutionize construction in space, using local resources on other planets. Of course, there are hurdles. Keeping the fungi alive long-term in harsh building conditions like dryness or alkalinity is tough. Scaling up production from the lab to industry cost-effectively is a major challenge. Current materials aren't yet strong enough for all load-bearing applications, and will need new regulations and public acceptance for living buildings. Despite the challenges, the potential is immense. Research is focused on improving survival, strength, and manufacturing. This fusion of biology, engineering, and architecture points towards a paradigm shift, moving away from inert materials towards dynamic, regenerative systems. We're looking at a future of sustainable buildings that are not just green, but truly alive, working in harmony with nature. The age of living architecture might be closer than we think.